We learned last time how to calculate the variance and standard deviation of a distribution, and I gave you an example of two distributions that have the same mean, but two very different standard deviations. Let's jump back in and take a look at the test scores for two groups of students. As you can see, the mean score for the two groups are identical. But suppose you scored an 89. Well, congratulations. In both classes, you would have done better than average. But which class would you rather be in? If you answered Class A, you're right. But why is this? Because in Class A, your score is higher relative to everyone else's score. Let's compute the standard deviation for these two data sets and see how that works out. Here I've used the summation table to compute the two standard deviations. One for Class A and the other for Class B. As you can see, there's a good deal more variation in the Class B data set. The standard deviation for Class B is 7.3, where for Class A, it's only 3.2. If you were in Class A and scored an 89, you were more than one standard deviation away from the mean, whereas in Class B, your score of 89, the same score, was only about half a standard deviation away from the mean. Another way of putting this is to say that your score of 89 in Class A was further from the mean relative to all the other scores than it would have been in Class B. Let's take a look at this graphically. Here I've laid out the scores along a number line and created a ruler that measures in units of standard deviation. The ruler is shorter in Class A because the standard deviation in Class A is less. One standard deviation in Class A is equal to 3.2 units, whereas in Class B, it's equal to 7.3 units. The red dot represents your score of 89. As the graph shows, in Class A, this score lies more than 1 unit of standard deviation away from the mean, whereas in Class B, it lies well within 1 standard deviation. We can look at this in another way, though. How about if we set up the number line so that rather than using units of scores, we use units of standard deviation? That's what I've done in these two graphs. As you can see, the scale we're now using is in units of standard deviation. That's why the length of the rulers is the same. Your score of 89 was more than 1 standard deviation away from the mean in the first class, but just a little bit more than half a standard deviation away from the mean in the second class. Put differently, had you been in the second class, your score would have been clustered close to everyone else's. In the first class, however, you were a bit of an outlier in a good way, since your score was higher. Obviously, this is a good thing. According to these graphs, in Class A, you're a real standout student. The scores in this graph are called z-scores. Z-scores express a score in terms of the number of standard deviation units it is away from the mean. That score of 89 in the first class is about 1.2 units of standard deviation greater than the mean. In the second class, that score of 89 is just over 1/2 of a standard deviation unit. It's actually about 0.54 standard deviation units. So why are these two z-scores different if the raw scores are identical? Because the standard deviations are different. Okay, so how do you go about calculating a z-score? Well, here's the formula. To calculate a z-score, you need the mean of all the scores in the data set and their standard deviation. From there, you use this formula. Simply subtract the mean from the raw score in question and divide that number by the standard deviation of all the scores. Just keep in mind that every raw score has a corresponding z-score. I've set up a table in the next slide to show you what to do. In the first example, we subtract the raw score 80 from 85, which gives us a -5. Divide that -5 by 3.2, and you get -1.56. -1.56 is the z-score for 80, a raw score of 80 for this data set. and 80 is about 1.5 standard deviation units away from the mean. You can see that a score of 85 over here has a z-score of 0. That makes sense because 85 is 0 standard deviation units away from the mean, which is 85. Negative z-scores are less than the mean. Positive z-scores are greater than the mean. And the smaller the z-score is, the closer it is to the mean. Just one thing to note here. If you figure this out yourself and compute the standard deviation yourself from the raw data, you'll find that you're going to get a slightly different z-score, but that's just due to rounding errors. If you use the 3.2 in this table, you'll get the same answer that I got. Why don't you pause the video and practice calculating some z-scores for this second data set for class B. I'll wait. Just pause the video. Okay, we're back. Here's the result of the first step. Subtract the mean from the raw score. If you need to, go ahead and pause the video again and try to do a few more. Okay, here's the finished set of z-scores. How did you do? Let's go back and take a look at the graph that we created last time, just to show you once again how this works. In this slide, we have the scores for class B, again laid out on the number line. You can see the calculated z-scores, and you can see graphically here where they're located on this number line. Again, the red dot represents a score of 89. And as you can see, if you look down this set of scores, that corresponds to 0.54 standard deviation units above the mean. How do I know it's above? Again, it has a positive sign. All right, just to recap, let's take a final look at this. So a z-score expresses a raw score in standard deviation terms. It tells you how far a score is from the mean score of a data set. Z-scores can take any value. A negative z-score indicates that the score is less than the mean. A positive z-score indicates that a score is greater than the mean. And the mean score in a data set will have a z-score of 0. We're going to spend a lot of time with these z-scores because they are essential in learning some of the inferential statistics techniques that we're going to cover going forward. I hope you found this video useful.